Hi, class. This is where we stopped, I believe. It was called Intermediate Products. I think this would be last page on your notes. And so we have this right here. We have if the limit as x goes to a of f of x equals to 0, and the limit of x goes to a of g of x is equal to infinity. So the question is, who's going to win who? Who is faster, basically? Is the thing that is going to 0 faster? And if it is, limit as x goes to a, g of x is equal to question mark. Like, which way is it going to go? So here it is. If 0 is faster as x approaches a to 0, that goes faster. Then if this guy's going higher, who cares? The 0 is going to win. But if the infinity one is going faster than this one, going down to 0, then this one wins. So it's really flat. Or they could actually just meet in the middle. They could be a ratio between the two. And so we'll talk about it here. Right. But I do want you to notice one little thing here. We talked about the interplay between them here, but I want you to notice one little thing right here. So these are called extensions of L'Hopital's rule, right? And so, but if you do this here, so f of x times g of x, if I'm going to make this into a ratio, right? So that means if g of x is on, the fx is on top, we'll leave that, and then we're going to put g of x on the bottom. The interesting thing is that true? If I put g of x in the bottom, I have to take the reciprocal of g of x. Does that make sense there? Dun, dun, dun. Right, let's go backwards. We're kind of doing this backwards from algebra, right? Sometimes we have like this. We have like 5 over 1 over x, right? And what we do is we keep the 5 as 5 over 1. No change here, right? We multiply by the reciprocal, right? Reciprocal of x. Notice as it comes in as a product, we have to take the reciprocal. So what we're going to do here is we're going to go backwards. We're going to say, look, if, okay, let's see, this is 5x, right? So let's go with this. 5x is the same thing then as 5 divided by 1 over x, which actually gets back to here. Whoa, that's cool. Right there. So we do the same thing over here. So as we make the g of x go into our denominator, we have to take the reciprocal of gx. What a fun little rule that was. Okay, but notice real quick here. This is the fun part here, is that f of x goes to 0. Is that true? Actually, no. So a few things here. It doesn't matter which one we stick to the bottom, right? We could stick the f of x to the bottom. We could stick the g of x to the bottom. It doesn't matter. But this is the cool part right here, is that what's the limit? I stuck a limit right here. What's the limit as x goes to a based upon what we have over here? This is going to go to 0. All right, that's what the limit was. And this one's going to go to infinity, but what is 1 over infinity? Just 0, right? As the numbers get larger on the bottom, 1 over a big, humongous, large number is 0. That's L'Hopital's rule. That's the 0 over 0 rule right there. Got it. Okay, how about this one here? What's the limit? If I stick in limit as x goes to a based upon the rules here, g of x goes to infinity. And then 1 over f of x, which is 1 over 0 now, right? Goes to infinity. So these are really just L'Hopital's rule. I would say this. This is L'Hopital's rule in disguise. I don't know if you heard that before anywhere. So, so the product is really just ratios or division rules of L'Hopital's rule. Cool. Okay, so let's start here. This is example 7. No, let's see what I got. So, example 7. Let's take the limit as x goes to 0 from the positive side of x times ln of x. Okay, so let's see, what are the limits here? Does it match the form? So off to the side here, limit as x goes to 0 from the positive side of x. And we need a graph of it here. Can we plug in the zero directly? Absolutely. We could plug in the zero. That'd be fine right there. Because if you can plug in the value, it doesn't matter if it's going from the right or to the left. It doesn't really matter for this, like in this one here, because um, you can plug in the value itself. That's kind of what you're looking for. And you know that x is a continuous function, so it is climbing to zero in the first place. All right, but this one, limit as x goes to zero from the positive side of ln of x. Now this one, again, just need another graph of it. Remember, what is the graph of ln of x? It's like this right here, right? We know that one. We all know that one. So as it goes from the right-hand side, we know it goes to negative infinity. Ooh, okay. This is, Maddie, this is what you mentioned the other day here. Does it matter if it's negative infinity or positive infinity? Just for the answer, it may matter. It may matter for the answer if you're going to go like to positive infinity or negative infinity. So, but the rule still applies. L'Hopital's rule still applies in that way. Okay, so let's go with it here. So limit as x goes to zero from the positive side of this initially is going to be the same thing as, and here's what we're going to do, just like we did on the previous slide. We're going to make this into a fraction between two numbers. Now, the question is this: which way do you want to go in order to make the easiest fraction, in order to make the easiest derivative? That's all. That's all we got here. And so to me, it kind of makes sense just to go limit as x goes to zero on the positive side, keep the ln of x on top, and I'm just going to put 1 over x on the bottom. So notice what I do. I do have to take the reciprocal as I take it down to the bottom. Okay, just real quick here. This is not part of the problem. This is extra, just for us. So the question is right here, is this L'Hopital's rule? As x goes to zero from the positive side of this guy, this becomes negative infinity. And this one's going to be, what's the limit as x goes to zero from the positive side of this? Well, that's going to be, as we said before, 1 over 0, right? So I'm going to put this in here. This would technically be 1 over 0, right? And then 1 over 0 really is infinity. And so, yeah, even though there's a sign change between them two, one's going to negative infinity, one's going to positive infinity, but that's okay. The infinity over infinity is still L'Hopital's rule. Okay, let's keep on going here. If that's the case, it fulfills L'Hopital's criteria to take the derivative. So let's take the derivative of each one. What is the derivative of ln of x? 1 over x. Perfect. What is the derivative of 1 over x? And this one, again, this one, you probably should memorize at this point. Let me get rid of one of my little thingamajiggies here. The derivative. So let's go off to the side here. The derivative of 1 over x. It is involving a quotient rule, but you should just memorize because it just happens so often right there. The derivative of 1 over x is negative 1 over x squared. All right, and if that's the case, whoa, hold on, we got an algebra equation in our hands. So off to the side, let's do some algebra here. So I'm going to do it up here. Let's see. So some algebra here. 1 over x over negative 1 over x squared will become, this guy stays the same. And we take the reciprocal of this guy multiplied by negative x squared over 1. And if that's the case, the simplified form of all that would just be this right here, negative x. Okay. Is that true? Some garbage truck coming in. Gotta wait for that guy to pass. Okay. So if that is true, all right, the garbage truck did pass. Okay, so with that involved, let's get this cursor here. Okay, so we get negative x. As before, awesome. Okay, now the question is, can you just plug in the zero? Absolutely, plug in the zero. negative 0 technically is just 0. So the limit as x goes to 0 from the positive side of x, ln of x is, and let me write it up here, write it as just, the answer is 0. Okay, looks like a donut, but anyways, it's 0. All right, let's go with it here. That's just one example here. That's just called the indeterminate products right there. Okay, I thought one example would suffice for this one here. We got to go on to another one here. And so now the question is this. We have something called indeterminate. And let me just fix a little something here. Okay. There it is. Okay. All right. Indeterminate. Now we have, those are products. This will be called differences. So question is, how do we look at differences? Let's go with it here. So limit as x goes to f x is infinity, and this one's infinity. Ah, okay. So let's think about this one. So then the limit, what happens when these two are subtracted from one another? That's our question. All right, so let's kind of do just a quick little view of it here. Maybe some simple example here. Let's say that f of x is x squared and g of x is x. Again, super easy example. So the question comes up is this right here. What's going to happen? And I'm going to do this. I'm going to say the limit as x goes to infinity. That's probably the easiest way to do it. Of x squared minus x. As this goes off to infinity, we can kind of even take a look at a graph of it, right? X squared minus x. Probably going to look something like something like this right here, right? The x squared in front is going to beat out subtracting off an x because x squared is more powerful than x going up. So notice x squared is trying to subtract, x is trying to subtract from x squared, but x squared is going to go up so fast, who cares? In this case, it's going to be infinity. But then what happens if I switch them around? So now I'm going to switch them around real quick here. I could redefine them. Now what's going to happen here? Who's going to win now? The x squared is going to win because it becomes faster and it's subtracting from x this time. So this side's going to go up to negative infinity because the x squared is going down really so fast compared to the x. All right, and then how about this one? How about if they're stuck? Sorry, I know I defined them right over here. Let me redefine one some more here. So I'm going to go like this. I'm going to say fx is equal to, let's go 5x squared. Just kind of thinking about something here. Let's see. Let's go 5x. G of x is going to be 3x. That's interesting. So notice there's like the same. So how much would minus 5 3x be? Yeah, in this case, you can actually even subtract them, right? The limit as x goes to infinity. And notice real quick, this is just 2x, right? What's going to happen here? That guy is still going to go off to infinity. Notice that's so interesting. So the 5x eventually draws it out to positive infinity. That's cool. Okay, are we good? If we can switch them around, that is going to go to negative infinity. All right, and then of course I'm going to do a little more trickier example here. This is going to be some trig forms here. But what's the form that we have here? The form that we have here is this one right here. So if we say, hey, what form are we looking at? Form is infinity minus infinity. That's what we're trying to figure out. All right, let's go. So example 8, limit as x goes to pi over 2 from the left side of the difference between secant of x and tangent of x. And I'll encourage you guys to graph these here. Let's go. So just let's go secant of x, right? As you approach pi over 2, it goes like this. Here's secant. Secant goes up to 1. It's a reciprocal of cosine. And this is pi over 2 right over here, right? So secant is going off to positive infinity right over here. Okay, so let me label this as f of x is equal to secant of x. Okay, and then tangent. Let's see what's happening with tangent now. Tangent goes like this. Hey, that is so weird. They're both going off to positive infinity right there. So this is g of x is equal to tangent of x. Now the question is this. This guy's going off to infinity. This guy's going off to infinity. Question is, which one's going off to infinity faster? Right? So technically, if secant goes up faster, then this whole thing would be positive infinity. If tangent is going faster than secant, this would be going off to negative infinity. If they balance each other out exactly perfectly, then we got ourselves 0 because they're just balancing each other out. And if there's a ratio between the two, then it becomes like 4. So let's do this here. So possibilities here. If secant is faster to going off to infinity, we got ourselves answer is infinity to this whole thing. If tangent is faster than secant, so this guy, because it's a subtraction rule, we're going to have negative infinity happening. If they balance each other out so perfectly that secant is going up, subtracting of the tangent going up, if it's just perfectly, they're balancing each other out, we're going to get a 0. And then sometimes, very rarely, but sometimes here, when these two subtract each other, but there's a ratio between the two, that means they are going up at the same time, but they're going up. So then you get like a number called 4, for example, right? So 4, or I should say like K, right? K is the thing. So let's try it. So let's write it out here. Let's see. So limit as x goes to pi over 2 from the negative side, which is what we looked at here, of secant of x. You just said, yeah, that goes off to infinity. Absolutely. Limit as x goes to pi, and I think I'm running out of room here. Let's see, tangent is equal to infinity. Okay, so we have the infinity minus infinity here. And so with that here, so let's go with it here. Does it obey L'Hopital's rule? Yes. So here's what we do with this one. We are going to do some work, and eventually we got to make it look like L'Hopital's rule. So we said secant is the same thing as 1 over cosine. True, true. Minus tangent. Tangent is tangent sine over cosine. This would be sine of x over cosine of x. We got ourselves our ratio. Hold on, look at this. The limit as x goes to pi over 2 from the left-hand side really is 1 minus sine of x over cosine of x. Okay, I'm going to erase all this other stuff here. I want to keep it. But at least I'll erase this part right here. So let me erase this part. The possibilities. Okay, but think about this here. And again, these are extensions of L'Hopital's rule. So whenever we put it back into a ratio, it better also work for L'Hopital's rule. So pi over 2, if you plug in that, for sine of pi over 2 is 1. 1 minus 1 is 0. Plug in a cosine of pi over 2, it becomes 0. There's my L'Hopital's rule. Again, sitting waiting for me right there. Always goes back to L'Hopital's rule. Okay, so that means we can take derivative of these guys. Help me out. Take the derivative of 1 minus sine of x. The derivative of 1 minus sine of x is negative cosine of x. The derivative of cosine of x is negative sine of x. Perfecto. The question is this now. Am I able to plug in pi over 2 to this? Let's see, sine of x, sine of pi over 2. Yeah, I can plug it in. Absolutely. So negative cosine of pi over 2 over negative sine of pi over 2. If that's the case, then we got ourselves, let's see, that goes to 0. That goes to 1. And then the whole thing goes to 0. That's my little symbol for something here later on. Okay, that is it, guys. So that means what has happened? They're going up the same time. They're pretty much just canceling themselves out each and every single time as they go up to infinity. That's what they're doing. Okay, the next part. Okay, so we got differences taken care of. Now we have indeterminate powers. Oh boy. So here's with powers now. All right. Limit as x goes to a of f of x to the power of g of x. All right. Now, what are the forms? Yeah, let's see. I'm going to change up my slides here just a little bit here. Okay, if that is the case, okay, so let's do this here. So one of three situations could be happening here. And so first situation could be that f of x is going to 0 and g of x is going to 0. And the strange thing about this one is if the base is going to 0, and then let's do this here. If the base is the winner, base wins everything out. And this is still kind of some kind of number. 0 to any kind of number is 0. So the second situation is this. What happens if the power wins? So let's say this is still this, and then the power goes to 0, like right away. We still have a number at the bottom. What's any number to the 0 power? It's a 1. Actually, I should put equal signs right here. So here's our situation. This guy could either go to 0 if the base is going faster to 0. If the exponent goes faster to 0, then we're going to get a 1 out of it. That's all. That's kind of what. And then that's the strange one. But let's do the other ones here too. There's 3 of them. Sorry. So just so you guys know, infinity and 0. That's the one that I really want to think about. Okay, so that's the. Okay, so what happens if this guy's going up? This is going higher and higher, and we get something going to 0. So let's see if the base wins. If the base is going up so fast that this cannot go to 0 fast enough, we're going to go to infinity. If the exponent is the winner, so yeah, this is some kind of number, but then 0 just went up to 0 super fast. Then we get ourselves same situation. So base wins out, we go higher and higher. The exponent goes out, we go to 1. All right, and this one, that's funny. So let's see if the base wins, what's 1 to any kind of power in the whole entire world? It's 1. If the exponent wins, and we're just going off to infinity super, super fast, then we got ourselves infinity. Are we good there? Okay, let me show you one little extra trick here. So part of the trick here is what we do is we let y equal all of this right over here. You may have recognized this from something called the logarithmic process for derivatives. But if we let that be true, and then we let this be true, what can we do with this g of x right here if it is ln of something? It goes in front. That's right, it goes in front. So now notice real quick here, this is just the product rule right here. This is indeterminate products. That's what we just studied. Let's see, that was the first, right? We did indeterminate differences, right? And we started off today with indeterminate products right here. So it really just goes back to a previous L'Hopital rule. That's kind of what's happening here. Okay, so let's do two examples. I'm going to do two examples here. Let's see what we come up with. All right, let's jam. There it is. So limit as x goes to 0 from the positive side of this. Whoa, that's some interesting stuff. There's some sine, trigonometric sine function, a 4x, adding 1 to it. Oh, tangent going to 0. I wonder what happens there. All right, so let's go with it here. So let's take a look at some graphs here. So if need be, let's kind of think through sine 1 plus sine of 4x. Now, the regular curve for sine is like this right here. Is all right? Boom, 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 like that. Okay, so if I put 1 plus sine of 4x, first of all, it goes a lot faster. And then what we do is our middle ground, right? Our middle ground now is, so it kind of goes like this. It's just going 4 times faster. It's bouncing between 0 and 2. But as it approaches 0 from the right-hand side, it gets to 1. So it looks like the form is going to be 1 here. And let's see about cotangent. Cotangent by the graph of cotangent does this. That's why we need to know these graphs. We should be able to recall them like, oh, yeah, that's right. That's cotangent. Cotangent is this. Cotangent, yeah, from the right-hand side, it's going off to infinity. So our form is 1 going off to infinity. What form is that from the previous slide? That's right. It is form number 3. Cool. Okay, so we can apply L'Hopital's rule here. So let's jam in applying it here. So let's write it out formally now, because we want to be formal. I know I'm going to write this in. I'm going to write form. What's the form that we get? Nah. Okay. Okay. I'll clean our here. Here it is. So for you guys to write on your sheet of paper, limit as x goes to 0 from the right of the base function goes to 1. The limit as x goes to 0 from the right of cotangent of x, or the exponent goes to infinity. So that is the form of 1 to infinity. Perfecto. Okay, how do we do this? Let's go with it. So what we're going to do is we're going to have y equals this whole entire thing that we start off with. This is a little bit involved. Let's take some time with it here. All right, we have defined y to be all this. So we made it into an equation so we can manipulate both sides of it. So what we do is we then say, okay, if that's the case, we could put ln on both sides at this point. Perfect. And we talked about it on the last slide here, that cotangent of x. What does that allow to do now? Since it's the power on a log function. So left side does not change, but the right side now becomes cotangent of x multiplied by ln of 1 plus sine of 4x. Now we just made it into a product rule, technically, right? Okay, so then the question is, can I make this into a ratio? That's what I want to do. Can I make this into a ratio? And again, we want to make the easiest ratio possible so we can make the easiest derivative possible. That's what we want to do. So cotangent, is cotangent 1 over tangent? That is so cool. So hold on. So that means this could be written as ln of y is equal to the top stays there, and the bottom, instead of writing cotangent, we just write tangent of x. That is so cool. Okay, so now let's do some algebra here together. So just got to be mindful of the fact that we're not taking, so L'Hopital's rule, we're not taking the derivative of the original function. We actually are taking derivatives of the ln of the original function. So let's write this in here. So limit as x goes to 0 from the positive side of ln of y, not of y itself, is going to be the same thing as the limit as x goes to 0. That stuff that we just made right there. I'll let you guys copy it down. And again, before we go on, extra, we don't need to mention this, but we should. The question is, what do I plug into here? Or let's see, does this fulfill L'Hopital's rule? That's what we wanted to know. So if I were to plug in a 0 into here, sine of 0 is 0. 1 plus 0 is 1. And what's happening to ln as it is approaching 1? That's my ln function. And as it approaches 1, the limit's going to 0, according to the graph. How about tangent? What happens to tangent as it approaches 0 from the right-hand side? Also 0. Hey, this one fulfills L'Hopital's rule. There it is. L'Hopital's rule is fulfilled. Okay. So there's my little. Okay, we can take the derivative. So let's see how we take the derivative of this guy. The derivative of ln of 1 plus sine of 4x is, or we can do this here. Let's see. A derivative of tangent. Derivative of tangent is secant squared x. Got that one. ln, remember that what we do is we make it into a fraction. On the denominator part is the same exact thing as the function that we originally started with. On top is the derivative of the function. So in this case, what's the derivative of sine 4x? All right, if you got it, it'll be cosine of 4x. And then because of chain rule, we're going to multiply by the derivative of 4x, which is 4 on the outside. Sweet. Okay. If you guys are okay with derivatives there, we jamming. All right. So now the question is this: am I able to plug in the 0 now into all of this? So I got two things to worry about, really. I got this denominator to worry about, right? Because the denominator of the whole thing, and then I got this denominator to worry about. And I can make, hopefully none of those go to 0. That's what I'm making sure. If the rest, the top can go to 0, just I can't have those two go to 0. So let's kind of think about this here. If I plug in a 0 into secant squared, what does that give me? Oh, that's right. That gives me a 1. All right, what do I plug into this one here? That gets me a 0, which really just gives me 1 over here as well. So you can write it like this. Some textbooks, what they do is they make you, because they see like, oh, that's a complex fraction, they make you simplify this first. And so if we were to simplify this first, we would say, oh, that's just this. And what we'll do is we're going to make it into a multiplication problem by flipping this upside down. Okay, right there. So if that's the case, we're going to have a limit as x goes to 0 from the right-hand side, really being this right here. So it's going to be, let me erase this little part right here. Boom, boom. That goes on top, and the two denominators become the product of the denominators right there. Okay, but can we plug in the 0 now? Absolutely. We could plug in the 0. So if we plug in the 0 to here, this would be 0 times 4, which is 0. Cosine of 0 is 1, and times 4. This one right here, we just talked about it here, 0 goes in here, sine of 0 is 0, but 1 plus 0 is 1. And secant squared of 0, so secant of 0 is 1 squared would still be a 1. So all this whole thing turns out to be a 4. Interesting. So as these guys go to 0, they're both going to 0, but there is a ratio of 4. The top value is going to 0 4 times faster than the bottom value, which is interesting. Okay, the only problem is we didn't solve the original problem. 4 is actually the limit of the ln of y, not of y, not the original function. So let's write this out on the next slide. Just say, okay, limit as x goes to 0 of this, which is the original function. Let's start off with the original function, and let's kind of work our way to what we know. And of course, there's like a little trick right over here. All right, so originally what we said, this was y. All of that was actually technically y. So this is the limit as x goes to 0 of y. If that's the case, then we're going to do this little trick. We're going to make y to be this right over here. Isn't that still y? Remember from algebra class, e and ln, they cancel each other out. So e to the ln of y really is just y itself. But there's a little trick right there. So that means this is the limit as x goes to 0. The positive side is the same thing as e to the ln of y. Now, do we have a limit for ln of y? Yeah, we do. It was 4 from the previous slides. That little piece right here. That little piece there. Ooh, let me do laser pointer. That piece right here we just discovered and we computed that. That was the limit of 4. So that means the whole thing, this whole thing, wow, that whole thing has a limit of e to the 4. That's the ratio that it ends up with as 1 plus sine of 4x is going to 1, and cotangent is going to infinity. Wow. All right, and let's go with the last problem of the day. Whoa, my laser pointer went away for a little bit here. All right, this is the last problem. Oh, let you guys write it down first. Go for it. All right, this one's just a little trickier for the last one here. So what form are we taking here? Oh, well, that looks like it is the form of 0 to 0, right? 0 to the power of 0. Okay, so let's go with this one here. What should we do here? Well, the trick. So let the base x, because there's two x's here. We've got to distinguish between the one that's the base. Let the one that's the base, we're going to make this to be x, just what we did on the last one here. Last one we did, it's going to be e to the ln of x. So it's the power on this whole thing, right? So if we put this as a power, so x to the x is going to be e to the ln of x, really to the power of x. Hold on, but the power on n ln really just is a multiplier. So e to the x ln of x. There's what we got, and we got it now as a product. So power on, and then look at this here. Let's see a little something here. Do we know from the previous example? Let's kind of think through here. Previous example, do we have anything that looks like this? Limit as x goes to 0 from the positive side of x ln of x. Look through examples here. Yes, that is example number 7. Absolutely. We already did this one. That is so cool. Okay, hold on. So this guy is just 0, right? That's from example number 7. We know that to be 0. So we didn't do a whole bunch of work. We didn't have to do a whole bunch of work here. That's cool. So let's kind of put this together now. So, and these 3 dots in as we're proving something in mathematics, it just means therefore. So therefore, as we solve this whole thing here, therefore, the limit as x goes to 0 from the positive side of x to the x is the same thing as the limit as x goes to 0 from the positive side of e to the x ln of x, which we just learned. All right, and technically E is just a constant, is that right? It's just 2.71828. So because that's a constant, we can move the limit rule into the exponent itself and work with that only. And then we found out from example 7 that that exponent really just goes to 0. So that's e to the 0. But what is e to the 0? And again, this is from the previous example, right? Previous example, which is example 7. And e to the 0, any number to the 0 power is 1. There it is. So unusual here. There it is. So that means as both of these guys are going to 0, technically the exponent has more influence. Right? Let's see if this makes sense here. As these guys are going to 0, if this was going to 0 faster, this would go all to 0, right? If this is going to 0 faster, it has more influence, then this means any number to the 0 power is 1. So in this case, the exponent has more influence upon this whole entire function of x to the x. And with that, that means we have a limit going to 1. Okay. Hopefully that settled you out with that one here, and then you're able to finish up the homework at this point. All right. Enjoy the weekend, and I'll see you guys next week.